Hello everyone, I'm Sarish Singh. I'm a PhD student at Columbia University and I'm going to be presenting my work, Surprising Privacy Threats from Innocuous Sensors. Now, these days, most mobile devices, including smartphones, smartwatches, and tablets, come equipped with built-in sensors like accelerometer, gyroscope, magnetometer, and whatnot. These sensors are often used by gaming and fitness apps to provide enhanced user experience. However, the privacy implications of several of these sensors have been previously studied extensively. Researchers have shown how carrying a phone in your pocket can be used to predict your gender and age, and even touching on the phone screen can be used to predict the age of the user. In this work, we show that these sensors gather sufficient data to quickly infer users' biological sex within a minute of holding the phone. And we also show that even a low-skill attacker without expertise in signal processing, feature extraction, or deep learning can succeed at gender prediction tasks. So the key observation behind our work is as follows. We see different patterns in accelerometer and gyroscope data in male and female participants when they hold their phones. The difference in the holding patterns between the user groups stem from users' hand stability, which is attributed to physiologic tremor. I'll talk a little bit in detail about the physiologic tremor, but let's look at the differences first. In the bottom of the screen, you can see we have a plot of accelerometer magnitude of a male and a female participant from our pool. Over here you can see the yellow line, which represents a female, has significantly less peaks and is comparatively stable when you look at the male participants. The male, on the other hand, has a lot of peaks and a higher range of data distribution. And these are the properties which are going to be helpful in classifying these genders. Now, physiologic tremor is an involuntary rhythmic muscle contraction, such as a heartbeat, which can lead to shaking movements in one or more parts of the body. Now, even at the moment, there are certain vibrations and fluctuations happening in our hand and our legs in different parts of our body, which cannot be measured just by looking at them. But if you have specialized equipments, lab equipments, you will be able to see that they are constantly moving. Now, this tremor is not actually a disease. It's a normal human phenomena that is a result of physical properties in the body of the user. Now, it's important to note over here that these patterns are subliminal, and it's very difficult to replicate these patterns consciously. Now, moving on, we present a threat model for gender inference task. It is as follows. The attacker wants to covertly collect marketable user information without the user knowing this data is being collected, right? Any mobile or web app that lets the attacker access the IMU sensors, accelerometer and gyroscope, functions as an attack vector. Now, these sensor data can be used to infer the gender in near real time on the app itself, or the data can be sent to the attacker and the attacker can perform the inference at their end. Now, these inferences might seem harmless, but they can potentially be used for data brokerage, political advertising that have far-reaching political and societal impacts. Prior studies have shown that women are more prone to be influenced by political ads. That is one of the examples. Let's look at the study design. We had built two apps, one for Android and one was a web app. Both these apps collect the data in the same format. We have 3 subtasks in each of these apps. The first one was the demographic survey, where we collect the ground truth such as gender, age, hand preference, income, etc. And the other task was a reading task, where a participant is asked to read a short article while we collect the sensor information in the background. The third task was for an attention check, where the participants complete a short quiz about how they have performed the study and some questions from the reading task. We asked the participants to use their own devices to avoid any bias of holding the phones, and we did not brief the participants about the nature of the study and the data collection. On the right hand side, you can see the high-level system overview. The participant is holding the phone. We gather the gyroscope and the accelerometer data. We extract some time series features, and we train the model, right? And the model is then used to make inferences. Moving on, so here's a summary of the data we have collected. In the first phase, we had 36 participants in the in-person study. We had 17 male and 19 female. In the second phase, which was completely online, we had 256 participants, 128 male and 128 female. And on the right hand side, you can see a table summarizing the general statistics of the user distribution. But if you look at the gender, you can see that male and female participants were almost about the same. And the participants were spread out geographically, although most stayed in the US or Europe. Now, the feature extraction phase. We actually extracted 4 different categories of features from the time series data. The first one is the distribution features, where we collected features such as mean, median, standard deviation of the raw sensor streams. The second we had extracted is the frequency features, where we capture where we try to capture and quantify the elements such as fluctuations in the time series, which can be captured by peaks. And then we have time domain features, which rely specifically on temporal knowledge regarding the data points. Examples of these include skewness and energy. And in the end, we had combination features, where we combined the features extracted from raw X, Y, and Z signals into one or more other features. In the bottom, you can see that we had a rolling window, and we extracted features from each of these windows, and then we trained the model on the extracted features along with the ground truth. For our evaluation, we used 2 different models, two different schemes. The first one was stratified tenfold cross-validation, and the other one is leave one out cross-validation. It's important to note that our primary goal is to identify the demographic attributes of one individual alone, and hence we emphasize the results of LOOCV. Also, to demonstrate that attacker does not need an expertise to perform this kind of attack, we use off-the-shelf machine learning algorithms available from scikit-learn library. We use 6 different algorithms, which are listed over here: random forest, KNN, SVM, naive Bayes, logistic regression, and decision tree. Let's take a look at the results. On the right hand side, there are 2 tables. On the top, it is a confusion matrix of LOOCV algorithm with random forest and KNN. In the bottom, we have the overall results with all the participants combined using the same scheme of LOOCV. And on the left hand side bottom, we have the table which summarizes the overall accuracies of all the 6 models that we had used. So basically, in the in-person study, we achieved an accuracy of 89% with random forest and 86% with KNN. In online only, we got an accuracy of 75.78% with random forest. KNN was slightly poorer than this. But in the overall, we had an accuracy of 78.46% with random forest, which I think is the best. You can see in the table that decision tree achieved 78.76%, but that is that was not consistent at all times. We also looked into the individual accuracies of each gender, and we saw that male had an accuracy of 82.06% as compared to only 74.83% for females. We plan to investigate this by doing a large-scale study. And then we have the results for tenfold cross-validation. You can see on the right-hand side, we plotted the ROC curve, and we can see the ROC curve of random forest is 0.8, and for KNN it's 0.72. For the other models, it was similar or lower than this. We also studied the minimum user interaction time required to make inference of gender. You can see on the plot on the right hand side that as you increase the time for the inference, the accuracy goes up. Basically, within 15 seconds of holding the phone, we can predict the gender with an accuracy of 74%, and after a minute or so, we can do it with an accuracy of 77%. But it's also important to note that you can get about 70% accuracy within about 5 seconds of holding the phone. It seems to be near real time. Yeah. To conclude, we presented a non-invasive transparent technique that infers the user's sex from the data streams of seemingly innocuous sensors. We also demonstrate that the interaction time needed to perform such an inference attack is within 1 minute. We provide evidence that even a low-skilled attacker can perform the attack that could potentially be used for data brokerage, political advertising, which have far-reaching political and societal impacts. And going forward, we plan to investigate a mitigation strategy and potential application frictionless authentication. Thank you for listening to me. Have a great day.